Welcome to the lair of the Batty Boffin.
Hi there Batty fans, welcome to another Batty Boffin video all about electricity. Now in earlier videos we looked at some of the main components of a simple circuit diagram. So before we go any further, here's a little recap for you. We've got some of the main circuit symbols. We've got a cell or battery there. We've got a switch which is currently in the open position there. An ammeter and a voltmeter and a filament lamp. These are two symbols you can use for a normal filament lamp, like a light bulb there. Okay, so what I'd like you to do is to draw me a simple circuit diagram that will just light up a bulb from a battery and then have an ammeter in it to see how many amps are flowing through and a voltmeter to see how many volts are flowing through. If you have no idea how to do this, go and look at some of the earlier videos, but if you reckon, have a go at that now please. Right, your diagram should look something like this one. We've got a cell here or a battery. If it's just one of them, it's a cell. If there's loads of them, it's a battery, but it doesn't actually matter too much for the diagram. You can do long, short, long, short, long, short, several of them if you want to, that's fine. Up here, I've got my filament lamp. Here, I've got a switch in the open position, and I'm just going to add my ammeter and my voltmeter. Now, an ammeter, if you remember, measures the amps, which is the units for current. So to measure how much current is flowing through, we're going to put our ammeter in series. That means it's part of the series of things that goes around the main wire there. The voltmeter, on the other hand, has to be wired up in parallel, which means these lines here that join it up are parallel to the main circuit. So there's my voltmeter wired in parallel over the lamp. So yours doesn't have to look exactly like this, but your voltmeter needs to be in parallel over the lamp like that, and the ammeter somewhere in the main series. So hopefully you've got something that looks like that. Now in this video we're going to be looking at the relationship between volts, amps and resistance. So before we go any further, I'd like you please to write down what these various things are. We have in this circuit the voltage, which is how many volts, for example, are being put out by that cell there to push electricity round. We have the amount of current, which is actually how much electricity is flowing round, and we have resistance, which I'm sure you know is futile. So voltage, current and resistance. For each of those, could you please list down the units that we measure them in? If you're not sure, check that out on some of the earlier videos. And if you happen to know the symbols that we use for them when we're writing formulas, then jot those down as well. But if you don't know those, don't worry, because we'll do those. So pause the video and do that now, please. Right, voltage is very easy. We measure in volts and the symbol is V. Dead easy. Current, bit more weird. We measure it in amps, hence an ammeter. Please note it's an ammeter, not an amp meter. I don't know why it should be an amp meter, but it isn't. It's an ammeter, A-double-M, ammeter. Here's the weird bit. The symbol for current is not C. Neither do we use A, although that's the abbreviation for the units of it. We use the symbol I to represent the current, and I have no idea why we use I to use current. C is, I suppose, used for capacitance, and I don't know. Anyway, it's I. There you go. Resistance, partly easy, part not. The units we use are ohms. Oh, the volts of the amps are A, and ohms are that weird omega sign. It looks like a smiley face with shoulders. Okay, and the symbol for it is R. So let's just have a quick recap. Voltage is measured in volts, abbreviation V, and the symbol in formulas is V for volts. Brilliant. Current is measured in amps, abbreviation A, and in formulas the symbol for the current is I, and I have no idea why that is. Resistance is measured in ohms. It's named after a guy, Mr. Ohm. And the symbol is in omega. Omega, whatever you want to call it. It's that kind of shape there. That's the symbol used for the units. And in the formula, we use R to represent it. So hopefully you've got all that. If you haven't, you need to know this. So write it down a few times, cover it up, try writing it down again until you've got that. Come back in a couple of minutes with a custard cream and a nice mug of coffee, because I'd really like a nice mug of coffee. I'll have wiped down the board and we'll give you some things to test these out and find out how they all relate to each other. Okay, back in a minute. Welcome back. Have you got your coffee? I've got mine. Okay. Here I've got our circuit diagram. We've seen this before, but I've incorporated an extra thing in it here, or a different thing. Instead of having a light at the bottom, I've got a resistor. This long thin box is the symbol for a resistor. And sometimes you can make them variable resistors. That just means it's kind of got a knob on it. You can turn it up or down to be different amounts of resistance. So that could be, you know, a 2 ohm resistor, or a 20 ohm resistor, or a 200 ohm resistor. So we've got our variable resistor there, which means we can fiddle around with it a bit. And we've got our ammeter and our voltmeter. And this is a set of 4 AA batteries, let's say. So they're putting out 6 volts. They're pushing around with 6 volts of force, let's say. Now, before we get too much into numbers, what I'd like to do is just have a think about what happens when you fiddle around with different things on here. So I've got 3 questions for you. One involving voltage, one involving the current, and one involving resistance. So the first question is, if you hold the voltage the same, that means you've got the same amount of pushing power going round. If you keep the voltage the same and you fiddle around with resistance, what happens to the amps, the current? So imagine this in the water analogy. If you've got a pump pushing amount with the same amount of force, and remember that this resistance is like a constriction in the pipe. Imagine you've got a hose pipe and you're treading on it, you're squeezing it. If you squeeze the pipe more, what happens to the flow? If you squeeze the pipe less, what happens to the flow? So that's your first question. Keep the voltage the same and fiddle around with the resistance. What happens to the current? Second question. Keep the current the same. So the amount of water in the water analogy flowing through the pipes needs to be the same. Okay? So the current has got to stay the same. What happens if you fiddle around with the voltage? What has to happen to the resistance? Or if you fiddle around with the resistance, what happens to the voltage? So to keep the same amount of water flowing, but you constrict the pipe, what would have to happen to the voltage to keep the same amount of water flowing? Okay, so the first question is keep the voltage the same, fiddle around with these. Second question is keep the current the same, fiddle around with these. Third question, keep the resistance the same and fiddle around with the others. So the resistance is going to stay the same. If you increase the voltage, what happens to the amps? Okay, so for each question, you keep this the same, find out what happens when you fiddle with these. Keep this one the same, find out what happens when you fiddle with the other ones, and keep the resistance the same, find out what happens when you fiddle with those. I don't need numbers in this, I just need to know if this one goes up, then this one has to go up, or if this one goes up, then this one goes down. It's that kind of thing I want. So, go and have a ponder. You need coffee, you need chocky bickies, or squash and marshmallows, or whatever it is that makes your brain think. By the way, your brain works on glucose, so you definitely need sugar for this. And so, go and have a think, come back when you've thought about it, and we'll have a look at those together. See you in a minute. Right, how did you get on? Hopefully, we should find out something like this. When you're keeping the voltage the same, so that's the amount of pushing power, when resistance goes up, if you increase the resistance, then the current goes down. So imagine that you've got a pump pushing water around. If you squeeze the tube, the flow of water decreases. So when resistance goes up, the current goes down. Okay? For the second one, keeping the current the same. If you have the resistance going up, in order to keep the same amount of water flowing through, the voltage has to go up. You have to push harder if you're squeezing the tube. So resistance goes up, the voltage has to go up with it. Or resistance goes down, voltage goes down, same thing. And the third one, keeping the resistance the same, so this doesn't change. If you push with more force, if the voltage goes up, then the current also goes up. Okay? Or voltage goes down, current goes down. Hopefully you found something like that. And those can, red pen, be beautifully combined into a very famous formula. It's called Ohm's Law. Same guy as that, very famous electricity guy. And he said that voltage is equal to the current times the resistance. V equals IR. And that is so important, it's going to get wiggly lines around it. V equals IR. Now sometimes you see that in different formats, and in other videos we're going to be using this to calculate different things. If the voltage is this and the resistance is that, then the current will be the other, whatever it is. But V equals IR, I think it might even need blue around it as well. Here we go. So get your highlighters out, write that somewhere big and stick it up. V equals IR. V, the volts, is equal to the I, the current, times the resistance R. Fabulous. Okay, I'll see you in the next video, Batty fans.